The simple stuff. I always screw up on the simple stuff. If it's complicated, then I kind of fix it. So hopefully everything's showing up decently there on everybody's screen. Should be talking about conductivity. So we're going to be talking about metal uh, and how things work in the ham radio world. So we're going to be talking about common metals used in the ham radio electronics and wiring. Uh, so we should be concerned about connecting copper wire to aluminum. So we'll be asking that questions and seeing how we do that, how we do it correctly without causing problems. We'll also be looking at what metals react to each other. It's kind of weird that you can think you can throw a couple pieces of metal together and you think that'd be a nice cool bond, but certain metals really, really don't like each other. And we'll be talking about what you don't want to clamp together, how how you might do this, and see what happens if you do it wrong. So we're talking about, is resistance, conductivity important? So we'll be thinking about certain metals conduct electricity better than other pieces of metal, and we'll be talking about those and how they stack up. Should you be worried about oxidations and rust? I think everybody knows what the answer to that one is. Yeah, you don't want rust. Um, so conductivity is expressed in Siemens. Mohs is another alternative name for Siemens, but it's basically nothing more than a simple resistance. Simple resistance. And Siemens is expressed as a reciprocal of resistance. So the formula is 1 over ohms gives you the Siemens. So an example of 5 ohms of resistance turns into 200 uh, millisiemens. And you can do that math real easy for you. So that's the most technical thing that you need to know about on this process. Let's talk about metal, conductivity of different kinds of metals. So this whole chart is all based on copper. Copper is the standard, usual, normal metal that we use for conductivity. Uh, I think hopefully everybody knows that silver is actually a slightly better conductor than copper. So it conducts about 105% better than copper, being 100%. Gold, we kind of think that gold is the gold standard for conductivity. Well, it's not. Gold is slightly less than copper. Aluminum is also a very good conductor. We use that an awful lot, but uh, aluminum has some problems with it, and we'll talk about that. So that is about the end of good conductors. Anything below that aluminum line is not so good. You know, we use zinc in an awful lot of things, and an awful lot of things are conducted in zinc, but zinc by itself is not a very good conductor. Neither is tin, and the other one is tin and lead. Tin and lead are not very good conductors, and we'll get into how they get used, that they actually save our bacon pretty well. But steel is not a good conductor. So you don't want to use large amounts of steel in whatever application that you're using for conducting electricity. Stainless steel, boy, we use a lot of stainless steel. That's really pretty important for what we end up doing in our ham radio community. And we'll talk about the right way of using stainless steel. But stainless steel has the property of not being very, it's not very conductive, but it also resists a lot of rust. So there's some good things about stainless steel that we'll talk about. To get things started, let's talk about plain old copper wire. So this is a good old chart here that shows different gauges of copper wire, how much resistance it has in ohms per foot. You know, per foot, it really doesn't rack up to much of anything. But when you take and start adding many hundreds of feet together, then that decimal point moves quite a bit on it. So 6 gauge wire, not much resistance. If we're working with solar powered systems, uh, energy coming off of solar arrays, we start looking very closely at the amount of losses that we have in our wire, trying to keep the losses to the absolute minimum that we can get the maximum yield out of our solar panels. And so there we have a lot of trade-offs between losses and throwing extra money at extra large conductors to minimize those losses. So we can see at a 6 gauge wire, don't have much losses. It basically, when we get up to our 16 and 18 gauge wire that is a lot thinner, there our losses start getting a significant amount, especially if we're going any distance at all. So for examples, here's a couple of examples. We're talking copper wire, 14 gauge copper wire, 100 foot of that gives us about 0.26 ohms of resistance. So that's not much. So that's pretty tolerable. For aluminum, and still that's considered a pretty good conductor, we get about 0.38 ohms. Now that compared to copper, that has a loss of about 37% over copper. So that is something significant when you want to compare aluminum and copper together. Now let's take a look at the really bad dude out there, and that's steel wire. Steel wire, 100 feet of that, 14 gauge, that gives you 3.25 ohms. So that's getting to be quite a bit. That's a 92% loss over using copper wire. Of course, there's a big, these days there's a big change in cost of doing things. So one of the things that all of this stuff, the big bad guy is rust that goes on. Now that rust and deprivation of the metal parts there comes from a lot of different, or several different methods. Some of it just comes from good old oxygen getting involved with it. Some of it could be acid that gets into it. Some of it could be electrolysis that gets into that. Well, that's a new one that we hadn't thought about. Down the lower left-hand corner, what happens when we connect a piece of copper tubing to some galvanized pipe? Well, if we don't have the right kind of connector in there, or that connector has failed, we can end up getting electrolysis, and we can get a whole bunch of corrosion that gets into it. And that's what that's what's happened. There's actually a plastic liner in there that keeps the two from making physical contact, but through the water, you can end up getting enough electrolysis that goes through there and causes a whole bunch of corrosion. Over on the right side, we have a breaker panel. So this is a breaker panel that's been oxidized, yeah, by probably salt water or something like that. In other words, just the salt in the air can cause things to oxidize like that. Well, what happens when it oxidizes? To the right of that breaker panel, you have a thermal energy or imaging of it, and you can see, oh, those breakers are losing heat. If you get heat in there, that means there's resistance. And if you get resistance, you're going to get heat when you start trying to move current through there. So there's a really good image of what that looks like for the power that's being lost there that going up in heat. Sooner or later, that heat is going to build up enough oxidation there, and it will cause a fire in that breaker box. Not good. So corrosion, that's the process that gradually destroys a refined metal. So that's the definition of what corrosion is. Gradual destruction of refined metal. That corrosion degrades the usefulness and property of the metal. Corrosion is usually a result of oxidation, a reaction with some kind of oxidant, such as usually oxygen. Now, that's one type of of process that goes through there and destroys some kind of refined metal. Another one that people don't really think about, we'll talk about that in some level of granularity, and that's galvanic. So that's popping two pieces of metal there that have very different physical properties. And these properties are actually electrical processes that go on within the metal. And that can end up doing the same thing as far as destroying the property of the metal. So let's talk a little bit about aluminum wire. Aluminum wire, back in the days when World War II was going on, copper was a premium and they needed copper for all kinds of processes in the war uh, arena. So they started using aluminum wire. Aluminum wires by itself is a pretty good conductor. It's not as good as copper, but when you have a shortage of aluminum wire, people use something cheaper, and that's good old aluminum wire. Now the problem comes about uh, between aluminum and brass or copper fittings. When you try taking aluminum wire and clamping into a brass connector or a copper fitting, you get this galvanic operation that produces oxidation. Add a little, add a little bit of moisture, heat, and expansion. Aluminum, depending on how much heat is it's been exposed to, it expands and contracts. So it has a big expansion coefficient along with the copper on it, and sooner or later that connection is going to not become secure, and you will start getting a reaction and some corrosion, and that will cause that joint to fail. So what did they do to fix this thing? They actually put together uh, a compound that allowed the two components to not oxidize. We'll get into that a little bit more. So dissimilar metals and alloys have different electrical properties. So aluminum and brass or copper have, and understand that brass is just copper with a little tin added into it. And it makes it not quite as soft as just plain copper. Copper is very, very soft by itself. So when dissimilar metals come together in contacts, one acts as an anode, one acts as a cathode. These are familiar terms that we use inside a battery. So that anode metal releases electron, breaking down or oxidizing metals. So as that anode releases those electrons, those metal pieces will start to oxidize and break down and start falling apart. The electric potential difference between the dissimilar metals is the driving force for galvanic corrosion. So those are two kind of metals that you just don't want to take and put together unless you do things right, and we'll get into that. So there's a whole process of galvanic potential. There's an index. Different metals have different galvanic things. So gold, you can practically put anything together with gold and it won't react. Well, gold is a little on the expensive side to do that. Also, silver really has a low galvanic index. But the problem with silver is that it also will oxidize very simple and very easy. When it oxidizes, it causes problem. Copper is another one that doesn't like different kinds of metals put together, especially aluminum. It starts reacting quite a bit. And brass being a cousin to copper, same problem. Chrome. I didn't think that chrome was a big deal, but actually chromium is a big deal if you take and mix it and trying to connect it with certain types of metal. Tin and lead are another two that you wouldn't think got together very nicely, but it actually they get together very nicely together. But bringing them together with other metals are a problem. That's why tin and lead go very nicely with silver and gold, but not so good with other things. Aluminum is also a really problematic thing that you have to pay special attention to when you bind it with different kinds of metal. Steel and zinc. Zinc is, it's a weird one. I still haven't quite figured out how it does so well as far as binding with different kinds of metals, but it does a pretty decent job. But steel is really by itself is really ugly. So the galvanic index is the difference in voltage between similar metals. Each type of metal produces has, you saw, has a different galvanic index, and that produces voltage by itself. So in a controlled environment, so if you're trying to build a product that is inside a house, that has a delta between these indexes of about zero point 0.5. If it's uncontrolled, so you have maybe a barn, it's kind of protected, but you still have other things that can get mixed in there and cause some problems with this uh, galvanic index. So there you don't want to build anything or put two pieces of metal together that has an index greater than 25 or 0.25. Outdoor, if it's outdoor, man, you got to have nice metals that really play together and they don't fight with each other. So preventing galvanic corrosions. Electrical insulation, isolation, electrically isolate the two metals using non-conductive metals. So if you have two guys that are going to fight together, like aluminum and copper, and you're going to bind them together, you can put a non-conductive material in between there that will keep them from fighting with each other. So ensure there is no contact with electro, electrolyte, moisture, water repels, water repellent compounds, greases, paint, and varnishes can help keep these things apart. Using antioxidants. So one of the things that I mentioned was good old copper and um, aluminum don't play together. So using an antioxidant to get with those two. And that's where how you end up getting those guys to play together. Works very nicely to keep the electrolysis from screwing things up. Choose metals with similar electrical potentials, like gold and silver goes really good together. Gold and copper go really nice together, but gold's always a pretty big premium. Electroplating. Here's another way where, in other words, you put thin layers of different kinds of metals together that by themselves or one into the other don't play together, but you kind of do a step process like gold, chrome, and nickel, galvanizing with galvanizing with zinc. So if you take and lay down, well, let's see, I got another slide here for assistance. So elements found in metal from the earth. Well, actually, it's, I guess another slide that coming up here. Gold, and so gold is something you don't have to process. When you find it in 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 the earth, it's gold. You don't have to break it down or do any refining to it. All you have to do is separate it from the dirt and stuff. Uh, Platinum is another metal that is native in Earth. You don't have to do any refining. Less resistance to corrosion. Zinc, tin, and manganese in cadmium are all ones that don't really, that has less resistance to corrosion when you put them together. Some metals from an ultra thin film of corrosion protection. So you can use aluminum, stainless steel, titanium, that's an expensive one, and silicon. But the two guys that I want to talk about in another slide coming up here is how we use aluminum and stainless steel. Stainless steel by itself is a really crappy conductor. Aluminum is really good. But how do we end up connecting these two together and making them play together? Plating process where you can use um, where you can reduce you can reduce corrosion between mechanical connections of dissimilar metal. So one of the things that you can do is, like, if you have stainless steel, it's pretty easy and it works really nicely where you can overlay that with a piece of copper or bronze, just a thin layer of that, and then overlay that with another layer of chromium or chrome. So that's the way you make a bumper. Trying to get chrome to stick to a steel bumper doesn't work. The two react to each other, and that's where you find bumpers with chrome falling off the darn bumper because something got in between there and allowed a galvanic reaction and allowed those two to fall apart. Galvanizing is another way of doing things where there you take zinc and you can get to bond to steel, and that zinc ends up preventing corrosions from happening. So here's some plating method. This is the slide I was thinking about. Silver conducts better than copper, used as a coating for copper to improve skin effect. So if you have something that, like a circuit board, you have copper that's laid down for conductivity. You can coat those um, where you make connection points with silver to provide some level of keeping the copper from corroding. You can also use on top of that, like for where you are putting a lead for that you want to solder, you can put gold plating on there. Gold plating works out very, very nicely on top of brass for allowing you to solder. I, uh, let's see, and then tin also provides corrosion protection for copper. So there's a couple of ways that you could end up using different things to keep copper from oxidizing. Copper or brass out there by itself oxidizes really, really thick. Brass, not so much, but pure copper for high levels of conductivity oxidize quite fast. Another one, zinc used to plate steel, prevents rust. So that's galvanizing, used all the time out there. Aluminum. So here's a good problem. Aluminum's always a problem. Galvanically very aggressive with direct contacts with copper or brass. So those two metals just don't like to get along with each other. So aluminum by itself, as soon as it's created, it produces a very hard layer of oxidation on top of the surface. So you have aluminum oxide on top of that surface. You can't solder to that surface, even if you try and weld to that surface. If you do not clean that oxidation off, you cannot weld to it. So if you're using a plasma torch and to try and connect to it, you have to remove that oxidized layer in order to get things to stick. So let's talk about to antenna. Uh, so you don't want to end up, you can't solder that wires out of that coax directly to your antenna because that antennas are always made out of aluminum. It just won't work. So you want to end up kind of soldering that antenna feed line. Let me get to the right point here. Okay, using solder rings, you really want to end up using soldering rings. So you can either crimp on or solder on solder rings, and then use that to connect to a balun, and then use that threaded connection with antioxidants. It's the same thing with when you want to end up connecting to your antenna. You want usually uh, um, some type of connector on there that you're connecting the rings for. Normally that is good old, um, come on, I'm trying to think of the right name for it, um, but anyway, let me keep going here. So copper cladding does not solder well. You may need to use a mechanical connection. So like you have copper cladded um, wire, like in a feed line, if you solder to it, usually that copper cladding on that solid metal wire will peel off. So you really need to use some kind of mechanical connection, such as um, a ring, clamp ring on it, or some way of getting that to your antenna. So let's talk a little bit more about aluminum. Aluminum for antennas is usually the 6000 series alloy, magnesium and silicon in it. That's usually the 6061 or 6063 type of commonly used for antennas. So if you want to end up connecting tubing together, most your antennas have some kind of tubing, and you want to connect two pieces of tubing together, you got to remove that oxidized level. And so the nice way of doing it is using Scotch-Brite to end up peeling off that tubing or peeling off that oxidation. And then you use a little bit of Noox or Pentex or no Noox or something like that on that connection, and then you clamp together. If you don't clean that surface off and you try and clamp it together, you end up with a big old fat open there, and that antenna is not going to work for you at all. You've got to clean that oxidation off before you clamp it together. Here's the one I was looking for. Connecting coax feed lines to antenna. So you always want to use some kind of a ring terminal on the feed line. So that feed line you usually crimp on, and generally you solder all that on there so it gets rid of any air voids. You have a really good connection there between your ring terminal and your feed line connections. So connecting the ring terminals to aluminum tubing using stainless steel nuts and bolts. Well, stainless steel nuts and bolts are not very good. So you want to make sure that path is as short as possible to get from your connection to that aluminum. That really helps. The smallest connection you can make, or the least amount of standoff you have there, the better you are as far as getting a good connection into the feed point of your antenna. Now, of course, before assembling all that, treat your terminals and stainless steel with some kind of antioxidant paste. And we went through the different kinds of stuff that you can use for that. Remember, stainless steel is not a good conductor. So let's talk a little bit about grounding. So antioxidant should be applied to all of mechanical connections, period. That's your go-to stuff. If you don't do it, you'll get moisture in there and you will get corrosion. And next thing you get is a high resistance and things aren't working right. So we know that towers have to be connected very, very well to a good ground. Never use aluminum in any part of a grounding system because aluminum will always, when you use in a grounding system, it will somehow it will end up failing and you end up with an open in that, and that's not good. Ground rod should always be good quality copper clad. Now, that's really hard to find a good grounding rod. These days, those darn steel cladded copper rods have a very, very thin coating of copper on it. And if your tower or antenna system gets hit with lightning, that's not enough copper. Usually that's not enough copper to conduct the amount of current that's going through it. And it just blows the copper right off the grounding rod and uh, tears up a bunch of other things. So look around, try and pay the extra bucks for a good quality grounding rod. Probably you're not going to find it at Home Depot. You might have to go to a real electrical supplier to find quality grounding rods. Use a brass clamp for connecting the grounding rod to your wire, to your grounding wire. I don't know if anybody has seen it. Well, here's a good one. I'm sure everybody's done a little hiking. They've been up to some kind of a fire lookout, and that tower has a whole bunch of grounding cables that come down along the wood structure and goes off to grounding rods into the ground there.
Mm.
And usually all of these are all connected together and they have this kind of bonding mechanism that uses the thing called thermite. And so thermite is used in all kinds of processes there, but they use uh, copper that actually uh, fuses to the copper braiding that for all of the grounding systems in that lookout tower. So
Mm.
thermite is always an extra super way of doing it, but it's pretty expensive and does take a little bit of special attention to know how to do that.
Hey, Mike.
Yo,
Yeah, I have a quick question, and this comes up in many circles for new and old hams. Oh, sorry, longtime hams. um, and that is grounding in this case is electrical and lightning protection. It's not meant to be part of your counterpoise for your antenna, right?
it's not meant to be electrical grounding for your house. We're talking about grounding for RF. So that ground, the connectivity is to our towers, to our antennas,
Hmm.
to our radios.
Right. Thank you.
So here's another one that people don't really think about, but towers are usually zinc coated. So all your towers are always galvanized. So we know zinc and copper don't play together. So never connect copper or aluminum directly to a galvanized tower. Okay, use a stainless steel. So that stainless steel is that kind of sacrificial metal that sets in between your wire that goes to your grounding rod and your zinc coated tower. So uh, you can get on DX Engineering and they have what's known, I don't, actually, I guess I don't know the right word for it, but it's basically, it's a piece of sheet metal that's stainless steel, and then you use, and you put a bunch of no-ox under that and wrap that around the leg of your tower. Then you take your grounding wire and put on the outside of that, and then put a bunch of no-ox on that too. But and then on top of that, you have another piece of stainless steel, and then you have a set of stainless steel clamps that clamps all that stuff together. If you don't do that, and you just take your wire and just clamp to your stainless steel tower, next thing you know, that zinc coating is going to start corroding and oxidizing, and it will eat a hole in the side of your tower on that on that leg there. So that's how you end up properly getting your uh, getting your tower grounded.
Mike, I have another question. Is that
Sure.
Noax and was it thermite that you were talking about? Are those conducting materials, or are they
Okay.
insulated?
Yes. Yeah. It is a conductive grease.
Okay.
So it conducts it. And the thermite basically fuses copper. In other words, it burns copper into copper for a mechanical connection. Actually, it's all one piece of metal. So there isn't any way of oxidation to get in there because it's all fused together. So got that about thermite? Thermite basically goes off in a great big flash and burns for a bit, creates a whole lot of heat, and then deposits um, copper around on copper. So it fuses things together. And also, there's different kinds of thermite. There's actually they use thermite to fuse railroad rail together. So that's a steel type of composite that they use there. So they have different types of thermite. You have to make sure that you're getting one that's used for copper. And again, on DX Engineering, you can find that stuff. So surprised this one here hadn't jumped out. Let's talk about soldering. So lead, tin, by themselves, those are horrible conductors. They are really poor conductors. So between electrical components and the circuit board etching, there's copper. So all that etching is all done in copper. So when you put a lead or a surface mounted device on that copper pad, and sometimes that copper is has coating. It may have um, gold on it or something like that. But there'll be some kind of coating on it that makes it a superconductor and super receptive for the um, lead tin combination. So that wire, the amount of distance that wire from that, let's say you're using a surface mounted piece, and the copper and where that lead tin fills in is just very, very thin. It's micron thick, thin. So that electrical current doesn't have to travel very far before it gets across that tin lead barrier. Same way on surface mounted components. That tin lead, you have a pad on that surface mounted component, and that distance that it has to travel across that tin lead barrier is very, very small. So the resistance is practically, it's a non-issue. It because it's so thin. I tried to make that point where if you're trying to take in like even on copper, if you like copper wire, if you have to run current for a long distance, you have a fair amount of resistance. If you're only running a foot, it's not much distance or much not resistance. If you're having to take and run just 10 microns, that's nothing. So it's no problems for those electrons to get across that tin lead barrier. Hopefully everybody understands that. Tin lead is a nice, easy product for us to use. It melts at a very relatively low rate, and it gives us a very good bond between the copper and uh, and the tin lead. So hopefully everybody got that. So, uh, so kind of, I could go on and on about a bunch of different things, but the main thing is that it's really nice. Okay, a couple of things when you go soldering terminals together. If you're crimping the terminals, you have a pretty good um, boundary. In other words, that's a good bite where you have copper and copper basically getting mashed together. And so it's not very likely that a whole lot's going to get in there. But if you really want to have a good bond, take that terminal and solder it because that will keep all the air and oxidizers out of getting into that terminal connection, and that will end up preventing any kind of corrosion. So that's about it. So any other questions or anything you'd like to mention here?
Mike, yeah. There's a couple of things. First off, I don't think you can say that the metals don't like to play with each other. I think it's the electrons on the metals that don't like certain to be on certain atoms. In other words, aluminum, zinc, all those highly oxidizable metals, they have. And if you remember that electrochemical series that you showed us, that chart with the propensity of a type of metal to, I guess, react or corrode. The lower down on that chart the metal was, the more the propensity was there, and then there was a number associated with that, which was the electrochemical potential, I guess, or some sort of index that they used. And the more negative it was, the more highly reactive it was. It's because the electrons on those metals, the outer electrons are they're not held that well to the nucleus, and so they can wander off very easily, and they might actually like being on copper or gold or silver or something like that, which are the more noble metals, because those metals, those nuclei hold on to those electrons much more tightly, and so that's why those particular metals are noble. They don't corrode, or at least they don't corrode easily, and the other metals do. So I think it's a question of like when you put those metals together, the electrons say, "Hey, I see a more fun spot for me to hang out, so I'm going to go over there." That's I think more how you can think of corrosion. The other thing is when we talk about the metal tubing, aluminum tubing for when you build antennas that are not wire antennas. Um, there's going to be a little bit of aluminum oxide on the surface, and no matter what you do, I think, and you're not going to get a. I mean, you'll get DC conductivity, but the RF conductivity could be quite high because actually you're getting capacitive coupling across the oxide, and it could be quite a low reactance there for RF. And so, despite the fact that you've got some, a passivation layer, if you want to call it that, or some oxide layer, which is quite thin on aluminum, it's still going to conduct the RF. So, despite the fact that you may not have taken any special measures to prevent the corrosion, a lot of people have antennas that are like that for many years, and they don't have any issues with with say an open circuit or whatever at the joints of those different metal tubes. So you can actually get away with that, I think, with aluminum in that respect. So
But wouldn't you say best practices is to clean that surface and treat it with a
oh
no-op, and then
yeah, I would agree that you might as well. But I'm just saying, if you didn't, I don't think it's the end of the world either. I don't know
you
of anybody who's had an issue.
well, okay, down in Grenada, we had a tri-bander up there, and every year when we went down there to do an event, we had to take that thing apart. We're try connecting. We couldn't get a decent SWR off. So we would have to take it down, pull all the fittings together. And this is, Grenada is right on the ocean there. We would have to take that thing apart, scrub all the connections, and re-grease it and put it back together. I don't know if it's one particular connection or if it was all of them, but um, when we took it apart, even with that dang grease, well, even with that grease that we had in there, it was not a perfect, it wasn't perfect. Now, maybe it'll only mess up on one band or something like that, but we just found that we just pulled it down, took it all apart, cleaned up every fitting, put it back together, or greased the fittings, put it back together, and voila, things started working again. We could get a decent SWR.
Yeah,
So,
I think in a salt air environment, you'd probably have a lot more issues.
yep,
Chloride ion is really corrosive.
yeah. And where we live in the valley with all the moisture, that's an issue. If you lived out in um, Bend or something like that, you probably wouldn't have much of an issue there. Any other comments?
Mike, you
Anyway,
always give us something to think about.
hopefully that gives you something to think about, and that uh, when you throw together a brand new antenna, um, or you get a used antenna. There for a long time, I was picking up used antennas and rebuilding them. I mean, it'd take me a week to go through there and clean everything up and put it back together and get it working again. But if one of them I took apart was just horrible, but it I did get it cleaned up and did get the thing operational. Now, even after all the work I did, I still only got 5 years out of it, and probably every other year in a contest, I burned something up in that antenna.
Oh, I have another question along those lines, Mike. Um, and this has come up on our technical discussion net on the W780 repeater. When usually we use stainless steel screws to attach the aluminum tubing together. And the questions come up about corrosion there. We have the screws attached to or touching the aluminum, and so people talked about using special greases and stuff like that. Um, so, what's your opinion on that?
I'd grease the fitting and grease the point where the screw goes through it
Okay.
to try and make sure that, because we also know with an antenna up in the air, that aluminum is moving, and over time that that point, that fitting will loosen up. So whatever you can do to try and keep the best amount of physical connection, the better off you are. And if you can just keep that joint from moving around, that would also help too.
Okay.
Okay.
Anything else?
Excellent topic, Mike. As always, some of the basics, we may not know them, but there's something to think about when you're trying to figure out what's going on with your antenna or checking it before you hang it. So thank you.
Yeah. There's a lot of science that goes into using different metals and stuff, but when you start looking around for solutions, there's always good solutions to do things.
Hmm. All right. Okay. We're going to go ahead and if anybody has any other topics, I'll start with one. Glenda, thank you again for pushing out the idea of a lunch gathering. I would encourage you to send a reminder email on the reflector so that people can go, oh yeah, that's right, it's this Saturday. So that would be my only suggestion. So Mike, did you have something else too?
Yeah, one other thing. 6 meters. That's that phantom band that sometimes is there, but usually not. And you just have to be darn lucky to get on there. But all day, 6 meters has been very, very wide open. It just closed up a few minutes ago, probably about 10 minutes ago, or at least it's down to a really small trickle. But it's 6 meters is a real hoot as far as getting things and not getting things, and when it's open, where you're going and stuff like that. Earlier this afternoon, it was open into Japan. I've had times where it's opened up to Europe. One time it was opened up wide open, 20 minutes, and I just knocked down contact after contact. It was absolutely wild. It was there, and then all of a sudden, 2 to 3 minutes later, it disappeared. So magical band, a lot of fun. I've been trying to get worked all states on it. I'm down to missing 3 states. Delaware popped up a little while ago, but I didn't have things turned on in the right place there to try and go after Delaware, and that was through uh, while the meeting was going on. So a lot of fun on that.
Thanks, Mike. Thanks for the alert. Anybody else? Otherwise, we'll go ahead and close it out. All right. Special thanks to Tom, our East Coast contingent there, for hanging out this
Yeah.
late at night.
It,
I don't want to be your alarm clock tomorrow morning.
we don't want to talk about 6 hours from now, but um, yeah, appreciate the discussion, and I will probably be back in the area sometime in August, and maybe you'll have something going on, and we can get
Yep.
together again. Appreciate it.
Yep.
Yep.
All right.
Yeah, well, I see you.
All right, take care.
All right.
Night.
Right.
Thanks, everybody.
Have a good night, all.
Yep.
Thank you, Paul. See you on Saturday, whoever's going to show up.
Yep. Yeah, I'll see you on Saturday if you're going to be there. Take care.
Bye.
Bye bye.